Welcome to this video. My name is Mark Scythian. The date today is August 28, 2024. So this presentation is going to cover solar and wind energy densities and their cost analyses. So we start out with a typical 250 watt DC solar panel, and so the sunlight will deliver 1,000 watts of thermal heat per square meter, and through the photovoltaic process 250 watts of the 1,000 watts input power is converted into equivalent DC electrical current like coming out of a battery, and then the AC power inverter at these generous efficiencies converts 90% of that DC electrical power into AC electrical true power. So 225 watts of AC true power, which is at the household 110 VAC at 60 cycles per second. So that is usable for household applications. Average cost $234 USD. And then we compare this to the typical commercial wind turbine, and that's 1.5 megawatts of AC true power at a cost of $3 million USD for the wind turbine. We have an average weight of 40 pounds per solar panel, and the average weight for a commercial wind turbine at 328,000 pounds. And so the specifications list 332 homes served. We're going to verify if that specification is accurate as well, and compare that to the 30 kilowatt hours per day consumption per house. So we got to focus on the 225 watts AC true power per solar panel on the solar power side here. So we know there's 1056 watts for every 1 BTU per second output in the form of heat regarding kinetic energy. So if we were to first figure out what that is in equivalent heat, the 225 watts of AC true power, it's equivalent to 0.213 BTUs per second with respect to potential energy. And so we can divide that into the weight per solar panel. And so we have an energy density of 0.005 BTU per pound for solar. And so we can compare that to the energy density of crude oil and all of its fuel derivatives. So gasoline is one of its derivatives. For example, gasoline has a fuel density of 6 pounds per US gallon, kerosene 6.75 pounds per US gallon, diesel 7.1, and then the gasoline has a 20,000 BTUs per pound times 6 pounds per gallon. So there's 120,000 BTUs per US gallon at a cost of $3.45. If we compare this to diesel, it is 19,500 BTUs per pound, kerosene 18,730. But if you graduate and equalize the fuel densities to the average energy density per pound of crude oil derivative, they all come to about 20,000 BTU per pound. So that is the base crude oil energy density. Okay, so now we just take the cost per solar panel and divide it into the usable AC power in watts, and we have $1.04 per watt with solar. And so if we were to set off 1 gallon of a crude oil derivative fuel such as gasoline, we'll use that because everybody's familiar with gasoline. If we were to set off a gallon of gasoline into combustion in 1 second, we would release 126,720,000 watts of power, equivalent thermal power. So that is still a valid power registry for comparison. So we just divide the cost per gallon of gasoline to equate the equivalent comparison to all crude oil derivatives. So you're paying $0.000000272 per watt with gasoline, or 2.72 times 10 to the negative 8 power dollars per watt. Okay, so if you can't legally build a commercially sold machine that runs off any type of crude oil fuel or hydrocarbon without completely reducing the crude oil or gasoline into carbon dioxide, water vapor, and trace amounts of oxides of nitrogen and oxides of sulfur, NOx and SOx. So it's not like it was 50 years ago where 80% of the fuel was consumed and 20% was unburnt gas. It was really terrible in the 1970s, right? But nobody cared back then, other than the fuel crisis and these types of things. So those countries that did not have their own resources, like Germany and Japan, they had this really advanced technologies due to the scarcity of resources. But the United States, even during the oil crisis, didn't have this problem. So nobody cared about this. It was just like, okay, if you can combust 80% of the fuel at low compression, and you had all this unburnt gas going in the atmosphere, that was an issue that is illegal to do today, but it was a very trivially recognized problem back then, right? So we can't compare like how it was 50 years ago. So all these engines, all these furnaces, they reduce through superheated catalytic conversion, including the carbon monoxide for the most part into CO2. And so if we were to compare the cost across solar to hydrocarbon fuel combustion, the solar is actually 38.2 million times more expensive. But stay with me, because there is the bigger picture of production mass cost and subsidies across a long-term financial plan. So it isn't just cut and dry. Everything's very abstract. So at face value, solar is 38.2 million times more expensive than hydrocarbon fuels, even though we look at it environmentally that we basically are controlling the emissions quite well, and I'll explain that point in a second here. So the average energy density of all hydrocarbon fuels is 20,000 BTU per pound. And so we have the solar cost per watt, $1.04 per watt USD. And so if we analyze the emissions of hydrocarbon combustion under legally sold heat engines and machinery running off fuels, the CO2 is the plant food, because that combines with sunlight and water so that plants incurs photosynthesis, and then the plants will then excrete oxygen gas for mammal survival, right? And then the greatest absorber and rejector of heat is actually the water vapor. That actually does play a role in global warming, because water absorbs and rejects heat the best. And then we have a moderate environmental risk with the NOx and SOx. Okay, so what are these solar panels made from? They're made from polymer, crude oil derived materials. So all of your polyester, nylon, plastics, and a million other things are coming from crude oil derived materials, not for energy in combustion, but for the structures and the materials. So we have to take that into consideration. And then we also have the manufacturing emissions in the process, not even including the combustion engines that are harnessing the electricity to run the solar factories. So we have to take these into account. Okay, so now we have at least a base comparison. All right, so there's like this bigger picture on how financing and subsidies pay themselves off. So this isn't pro and con. This is like just the big picture with respect to the comparative analysis. Okay, so now we take the 1.5 million megawatts of AC electrical power that each commercially sold wind turbine can harness, and we divide that into 1056. So that's 1420 BTU per second in equivalent heat. Okay, then we divide it into the mass of the wind turbine unit. Okay, Okay, so we get 0.004 BTU per pound energy density, whereas crude oil has 20,000 BTUs per pound energy density. Okay, so from that point on, we can just get a base value on the linear cost comparison between wind power and hydrocarbon fuel power. And so it's about 50 million times more expensive to harness energy out of the wind turbine compared to hydrocarbon fuel. And then we have to take into consideration the wind turbine is constructed from steel and from the steel factories and their electrical power grid running mostly off combustion power plants, hydrocarbon combustion power plants. We also have oil derived materials, including the polymers for sure. Glass fibers, not so much. Those are more like quartz, and composites, a little bit of the oil derivatives, and like carbon fibers. Nylon is an oil-based substance as well. So you may have carbon, nylon, and glass fibers making up the blades. And then the electrical structures are including the epoxy laminates to laminate stators and etc. So there's a substantial amount of oil materials made from the electrical structures, but that also includes rare earth metals for the neodymium magnets, etc., and iron and all these types of things. So we do have a substantial amount of resources to build a wind turbine other than crude oil. And then, of course, 3 is oil-based, and then we have oil-based electrical power needed to build the wind turbine. So that comes down to a cost per watt with the wind at $2 per watt. Okay, so if we just use gasoline as the metric for the base value of hydrocarbon fuel density, that's 120,000 BTUs per US gallon. Okay, so we'll enter that in. Solar power has an energy density of 0.005 BTU per pound, costs $1.04 per watt. And so if we make this equivalent to the hydrocarbon fuel power, it comes to the 2.72 times 10 to the negative $8 per watt. Okay, so we have that documented, and then solar power 38.2 million times more expensive than hydrocarbon fuels. So we have to take the initial specification, and this is where the controversy is, where they rate a wind turbine for so many homes, but then when you do the analysis on 30 kilowatt hours per day, so that's 30,000 watts divided into 24 hours, that's 1250 watts times 1 hour for 24 hours. So that's where we get the 30 kilowatt per hour per household average use in the United States. So if we were to take 18 watts per household delivered by the wind turbine and divide it into 1250, we actually could, at a base minimal value, power 1,200 homes off a commercial wind turbine rather than 332. So a lot of that may go to overhead, transmission lines, underground wiring, etc., and then they downgrade the amount of houses that can be powered off a wind turbine. And that is where people get kind of an uproar in the city council meetings, because they'll bring with them somebody from the power company or hire their own engineer, or etc., and they'll say, you could get 900 homes out of it. And then the city will be like, oh, well, we have to get paid too. So there's all these other things, not just the equipment and the technology and the electrical power. So, it's a regulatory rating, 332 homes. But technically, if we didn't cover all of the other infrastructural costs, you could power 1,200 homes off one commercial wind turbine at 1.5 megawatt AC power rating. So if we take the 30 kilowatt per hour per day times 365 days, that's 10,950 kilowatt hours per year per home in the US. And so we have to compare that to the fuel combustion cost. So that would be 1,250 divided into a thermal efficiency of 30% average combustion engine 4167 watts of fuel combustion per year per household. And that includes natural gas. It's an equivalent derivative. If you scale all the energy density and fuel density together, you get about the same 20,000 BTU. For example, a pound of natural gas is 24,800 BTUs. It looks like it has more energy density, but then its fuel density is much lower, 0.041 pounds per cubic foot. So it comes back down to all about 20,000 across all petroleum, or I will say hydrocarbon derivative fuels. And so that's 4167 watts fuel combustion, like in a furnace or an engine, etc., times the 2.72 times 10 to the negative 8 power dollars per watt. And then we have this value taken as the cost per second to operate that in fuel combustion times the 3,600 seconds to an hour times 24 hours times 365 days. So that comes about $35.74 per home using fuel combustion sources of energy. Okay, that's hydrocarbon sources, right? Okay, so now if we only had the 332 home rating per wind turbine, commercial wind turbine unit, that price increases to $9,036 per household or home with the wind turbine. So we have to take into consideration the long-term pay down cost, and of course if there's a government subsidy, then the taxpayer is paying for it. So we have to know the source of that money / energy, where's that coming from. But this is where we have one more metric left, is the average. So average of 30 solar panels per home at a decent price of $234 per solar panel. We have the AC inverter, the installation cost, the taxes and fees, etc. And so that comes to a reasonable average of $11,720 per home minimum. So we have these values set together, but a very interesting part of the analyses, as in two or more analysis is an analysis, is that the solar power is 38.2 million times more expensive than hydrocarbon fuels by unit of production mass. Okay, we're talking about every molecule required to make these technologies. So that's a base value of 38.2 million times. One may argue it would take 38.2 million taxpayers to pay for 1 million solar users, but it could be, but it's not necessarily that linear relationship. So solar power is 38.2 million times more expensive than hydrocarbon fuels by unit of production mass inside of long-term subsidies and taxpayer financing. Production mass is applicable. Okay, so we got to compare that to wind power, which is 50 million times more expensive than hydrocarbon fuels by unit of production mass. We're taking a weight of the fuel and the weight of a commercial wind turbine, and we're getting its power output over the weight. So again, that is a base value. But then again, the wind power is outside, not inside, but outside of long-term subsidies and taxpayer financing. So therefore, the production mass cost is not applicable. So the big controversy with the wind power is how many houses do you rate a wind turbine unit, a commercial wind turbine unit to. So if they're doing just a 332, then we have $9,000 per home. And if we go to the base value, 1,200 homes, where we exclude the infrastructural costs, then $2,500 a home. And then actually it's cheaper in the long run to go with wind power, but a reasonable would be somewhere in between that. So let's say 800 homes, and you're about $6,500 per home. And if you could get that a little bit better, maybe 500 homes or so, then you get the same amount of cost with hydrocarbon fuel heating. It's usually heating and natural gas, etc. either the fuel's heating or it is the just the general gas turbines at the power utility unit, or their steam turbines, the natural gas heating, the water for steam, etc. And so it comes to about $3,500 a year in fuel costs, and that doesn't even account the infrastructure costs, the taxes. So you're between $3,000 and $5,000 a year, and the solar is 11 to 15, and then the wind is between, let's say, 2.5 and 5. So in the long term, if there's a pro and a con, it is not always good to take a side with the technology. But if you were looking in the long term, then the wind power is kind of a bit of a winner. But see why this is getting a bit, I don't want to say complicated, but it's getting a little bit more on the abstract calculations, is due to the fact that the energy densities are not so cut and dry and practical like is so with the crude oil. And so then we have to do all these things to scale up, scale down, use tax subsidies and taxpayers to invest in long-term funding and et cetera. But in the long run, if you have a wind turbine that has a long maintenance life cycle, has a long life cycle minimum maintenance, then it could more or less pay itself off if the maintenance was ergonomic, like it wasn't too difficult to do the expenses, and you plan, you zone the wind turbines in the right area, and then you kind of get about what you're spending with fuel in the long run, of course, not in the short run, not at all. And so that's where there's this polarization, what is better, what is worse. But reason why it's like this is because the energy density just isn't there with all of these technologies on the alternative side. And that's why people in business are not going to waste a whole lot of time, at least they haven't, on what is the quick solution. The consumer market wants convenience, instant results, and it's going to be in the crude oil, because look at the energy density, it's so massive in the crude oil. And so how you burn that crude oil, if you could reduce it down into acceptable emissions, etc., plant food and water basically, and a little bit of SOx and NOx, then it's actually a pretty emissions reasonable application. But it doesn't mean it has to stay like that. So is there like a simple solution? Is there some resource that leads to ease of use, cost effective, massive energy density? And actually there is, and I wanted to cover these last two so that I can get to that video following this one. And I'll kind of make a list of all the different conventional and alternative power technologies, their energy densities, and then cut to a solution that probably is actually going to be implemented in the future. I don't know if they're going to be so straightforward about doing this, but I think when more people gain the scientific understanding other than engineers and scientists and people in STEM, it will become more socially acceptable to move to this particular resource because of its massive energy density, and its containment is highly controlled. So that's why it's so safe. But at face value, if it wasn't contained, it would start to become something you couldn't work with directly. So I'll cover that in the next video. But this one is kind of the last analyses. I had to put two of them, analyses on the solar and wind, and this can be tied across to the previous technologies. And so the next video I'll get into the highest energy density, most likely solution to harness clean electrical power from. So I'll see you in that video. Thanks for watching this video presentation, and have a great day.